How we think about energy in cells. In this first video, we'll define energy, showing how it's stored in the chemical bonds within molecules. We'll show how energy is quantified as free energy in living cells. Then, we'll classify reactions as spontaneous, exergonic, catabolic reactions, which break down molecules and release energy, or non-spontaneous, endergonic, anabolic reactions, which build up molecules, requiring energy. By understanding energy in chemical bonds, free energy, and the various ways we classify reactions, we will be prepared to deeply understand the roles of ATP and enzymes, which we'll cover in the next video. Energy is the capacity to do work. Unstable systems hold more potential energy, stable ones hold less. Which of these two towers is more likely to collapse? When a tower falls, it moves and does work. So an unstable tower has greater work capacity than a stable one. As systems drop to a lower energy state, they release that excess energy. For example, a ball atop a hill stores gravitational potential energy and releases it as it rolls down to rest in the valley. Chemical potential energy is stored in covalent bonds. For example, the carbon-carbon bonds in glucose and the phosphoanhydride bonds in ATP. When bonds break or form, matter and energy shift. Enthalpy is bond energy. Forming bonds stores energy. Breaking bonds releases it. Entropy is energy dispersal, meaning energy spread or disorder. Splitting one molecule into two increases disorder like managing 10 toddlers instead of one. Merging molecules reduces entropy. In short, enthalpy is linked to bond count, and entropy is linked to molecule count. Breaking bonds reduces bond count, but increases molecule count. Forming bonds increases bond count, but decreases molecule count. In chemical reactions, we track the free energy change known as delta G. The triangle delta means change, and G is the energy available to do work. So delta G represents how free energy changes across reactions. A positive delta G means the reaction needs energy, like kicking a ball uphill. It won't go up unless you kick. We call this non-spontaneous. A negative delta G means it releases energy, like letting that ball roll back down to you. It rolls down on its own. We call this spontaneous. We quantify free energy change with this equation, but don't worry, we're not doing any math. Delta G equals delta H minus T times delta S. Here, delta H is the change in enthalpy or bond energy, and delta S is the change in entropy or molecule count, with temperature T scaling entropy's effect. Forming bonds raises enthalpy and lowers entropy, increasing delta G. Breaking bonds lowers enthalpy and raises entropy, lowering delta G. Reactions fall into two camps. When delta G is positive, the reaction is endergonic. En means entering, and erg means work. The same erg you know from the word energy. So endergonic literally means entering work. Energy is required, and the reaction is non-spontaneous. It won't happen without that energy. When delta G is negative, the reaction is exergonic. Ex means exiting. Energy is released, and the reaction is spontaneous, or runs on its own. In cells, reactions that build larger molecules from smaller ones are called anabolic, like anabolic steroids build muscle proteins. Anabolic reactions form chemical bonds requiring energy, and so are endergonic. For example, amino acids link into proteins, fatty acids and glycerol join into triglycerides, CO2 molecules combine into glucose in photosynthesis, and ADP and phosphate unite to form ATP. Reactions that break molecules apart are called catabolic, like a cat that shreds your furniture. They cleave bonds, releasing energy, and so are exergonic. A classic example is the stepwise breakdown of glucose during cellular respiration. To visualize energy changes, we can use reaction progress graphs. Let's look at one. Reactants start on the left, products on the right. If the products sit higher than the reactants, an uphill climb, delta G is positive and the reaction is endergonic. If they sit lower, a downhill slope, delta G is negative and the reaction is exergonic. The hump is the activation barrier, an energy peak representing the unstable transition state between reactants and products, or the puberty of reactions, if you will. Molecules need a burst of energy to climb this awkward high energy state. Then, they either revert to reactants, or if the energy is enough to overcome the barrier, they proceed to products. Half-formed bonds can't persist. They're simply too unstable. So every reaction, whether endergonic or exergonic, has an activation barrier. In the next video, we'll explore how these energy principles apply to life's reactions via enzymes and ATP.